Majority of students end up in many colleges across the country, and quality varies a lot from college to college. What should a premier educational institute like IIT Madras be doing? And NPTEL is an answer to that.
NPTEL is an online courses or a MOOCs platform. We can call it a revolution in online education.
Today, nptel.ac.in, our website, is one of the largest repositories of engineering content in the world.
The type of students that we are able to reach is a fairly broad spectrum which goes into this idea of lifelong learning.
NPTEL with the local chapters is actually a very collaborative environment in which we want to cooperate and work with the colleges rather than being a competition for them.
Wherever you are, whoever you are, if you're interested, you can learn.
The Institute of Eminence scheme has been launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the select institutes of excellence. As part of our commitment to the cause of fostering world-class research, IIT Madras has set up a number of research initiatives in diverse fields of contemporary relevance. Many of these initiatives will go on to become centers of excellence within the IIT Madras system. A total of 68 research initiatives belonging to 21 identified technology clusters are presently underway. As part of these initiatives, it is proposed to host a series of webinars from each cluster to showcase the innovative research being generated to various stakeholders like researchers, industrialists, and policymakers. These webinars will give an opportunity to engage in conversation with eminent faculty from IIT Madras and other international researchers, and also to find more collaboration in those research areas. So why wait? Click the link below to be a part of this.
Thanks for the lovely video, Shivram. That was a very good collection that we have. Very good evening to everyone who present virtually through Zoom and YouTube. So this is Rudra from the Office of Global Engagement, IIT Madras. The Institutions of Eminence scheme has been launched by the Government of India to empower higher educational institutions and help them become world-class teaching and research institutions. IIT Madras is proud to have been selected as one of the select institutes of excellence. So a total of 68 research initiatives belonging to 21 identified clusters are presently underway. As a part of these initiatives, it is proposed to host a series of webinars from each cluster to showcase the innovative research that is being generated to various stakeholders like researchers, industrialists, and policymakers. And that's how the IRIS webinar has started, and it is running very successfully. And it is my pleasure to welcome you all for this 35th webinar of this IRIS webinar series. So today's webinar is on carbon dioxide capture, utilization, and storage under the cluster Energy, Propulsion, and Renewables. So this research initiative project is being led by Professor Preeti Agalyan. And I can proudly comment that this is one of the projects which has more than 14 eminent professors from the Department of Chemical Engineering, IIT Madras, who are very actively working in this project. So I take this opportunity to welcome Professor Preeti Agalyan, Professor Nikit Kaisare, Professor Rajnish Kumar, Professor Jitin John from the Department of Chemical Engineering, who have joined in this panel as the speaker. So the moderator of today's program is Professor Praveen Linga. To introduce Professor Praveen Linga, he is currently the Vice Dean for Communication and Outreach at the Faculty of Engineering at NUS Singapore. His research interests are in the areas of caltrate, hydrates, storage and transport of fuels, carbon dioxide capture, storage and utilization, seawater desalination, and recovery of energy. So he is recognized among the world's most influential scientific minds and highly cited researchers in engineering by Calvete and Analytics. So he is the Fellow of Royal Society of Chemistry. Currently, he serves as the Associate Editor in the Energy and Fuels Journal. He is also an invited editorial advisory board member of the following journals: Advances in Applied Energy, Current Opinion in the Chemical Engineering, Fluid Phase Equilibria and Processes. So it's my pleasure in welcoming you, professors, to the session. Over to you, Professor Linga.
Thank you, Rudra. Preeti, you're going to do the introduction.
Yes.
Yes, please go ahead. Yeah.
Niket, if you can share the slides. Okay, a very warm welcome to all the attendees. It's genuinely an honor to be sitting here in the 35th webinar of the IRIS series with such a distinguished set of panelists as my colleagues and Professor Linga here. We have titled today's presentation as Tackling Wicked Problems. When we think of problems that are really convoluted, difficult to solve, that need a massive effort from the brightest minds, when you think of a problem like that, the problem of carbon dioxide definitely comes to mind. That is what we have picked in this team to tackle. And the technical details of it will be gone into in some amount of detail given the time constraints by my colleagues. But I just want to tell you that we have a number of strategies that we think guarantee us success. First of all, as Rudra also mentioned, we have a very large team. We have more than 40 people already onboarded for this initiative. Very diverse. There's more than 10 of us professors. We also have a number of staff. We have lots of students, postdoctoral researchers, you name it. We have a diverse group over here at CCUS lab. We've broken down the problem of carbon dioxide for the country, for the world, into 4 different verticals. And we have lots of ideas within each of these, which is what is going to be the subject of the rest of this talk. We would love to stay connected with all of you, whether you're students looking at a career or research career in this field, or even younger students looking at just dipping your toes in here, or with industry partners that would like to work with us. We would love to be connected with you. So please reach out to us. We'll be very happy to speak with you about the ideas that we have. And one thing we do as a team is celebrate all the small and big wins that we have. And today's webinar is definitely one of the wins that we have on our calendar. Team is very large. Here I've only put the faces and little bit of expertise of my faculty colleagues. You can see that young and old, there are plenty of people, but we will not go into each of the expertises. Suffice to say that we span everything from atomistic scale simulations to very large field scale experiments, from computational work in various fields to very detailed experimental qualifications as well. With these few words, I think I'll go to my last slide, Niket, and welcome you all to enjoy our webinar. I'm pretty sure you'll have tons of questions. We'll be very happy to take it after we finish with the technical part of our presentation. Over to you, Niket.
Thank you, Preeti. And I'll start the technical part of our webinar. So we have titled the talk as Process Development for CO2 Capture, Utilization, and Sequestration. A quick slide on why this is an important problem. These are the various sources of CO2 emission. Transport and electricity is, of course, the highest, which contributes to slightly more than 50%. And if we look at the amount of investment that we need over the next 3 decades, for example, US requires an investment of approximately $4.5 trillion in order to decarbonize the power grid. Germany requires slightly more than $500 million. And India's production, although it's not as much as US right now, but it's expected to be 5,000 BUs in the next 3 decades. So we will have to make significant investments. There's no silver bullet, as they say. The solutions are going to span various different areas, and the area that we are interested in is the CO2 capture, utilization, and storage. So what are the sources of CO2 emission? Power plants, industries, vehicles, farms. These are the typical examples. And what do we mean by capture, utilization, and storage? We mean capturing at the source, for example, capturing from the power plants, transporting them to the places where they need to be sequestered, which means we can, for example, as shown over here, we can put it under the seabed as a part of the sequestration. There are various different alternatives to that, or utilize it through some kind of conversion or through non-conversion based approaches, something that we are going to talk about very briefly in a few minutes from now. Let me now focus on CO2 capture. So what are the ways in which you can capture? So CO2 is basically generated. Let's take an example of a plant where CO2 is generated. You can capture the CO2 before CO2 is generated. You can have strategies to improve the combustion efficiency so that you have less amount of CO2 generated. You can have a peak CO2 capture, which basically means that you burn hydrogen, you convert your fossil fuels into hydrogen and pre-capture the CO2 and only burn the hydrogen for energy generation. Or let's say you have biofuels. In biofuels, you can separate out CO2 and methane are important components of biofuels, and you can separate them out. In all the cases, the thing that we are focusing on is how to capture, which a synonym for this that we use is how to separate CO2 from a multi-component gas mixture. And these are the challenges that are listed over here. So you have CO2 separation from nitrogen or oxygen separation from nitrogen in case of oxy-rich combustion. You have hydrogen to be separated from CO2 in pre-combustion capture, and you have methane to be separated from CO2 in case of a bio or natural gas capture. Okay. In all of these cases, we need to understand how does CO2 behave in comparison with the multiple different components that it is present simultaneously with. And that is one of the areas of interest to the CCUS lab. Okay, and the technologies for CO2 capture, we can have physical adsorption, cryogenic distillation, membrane diffusion, and chemical absorption or adsorption. Our team focuses on physical adsorption, membrane capture, and chemical adsorption processes. We do not yet focus on the cryogenic distillation part of the technology. Okay, and this very quickly to go into a little bit of technical details, we have experimentalists as well as simulation people. On the left-hand side, I'm showing some examples from experiments, and the right-hand side, it's some simulation results. And the results span a wide range of scales from atomistic, molecular, mesoscopic, device level, as well as system level. So we are trying to address the problems at different levels, combining experiments and simulations in order to try to solve this difficult problem of CO2 separation. So that is the final slide that I have, and I'll hand over to Professor Arvind for utilization of CO2. Arvind, over to you.
Yes, Niket. So I'm just trying to maximize my screen. Somehow all my screens went small. I don't know why. Yeah, now I got it. So I hope you could hear me. Just Niket, could you please confirm? Oh, great. Thanks, Praveen. So CO2 capture is one thing, and then converting them to useful fuels or any value-added products is the second most important thing. So we cannot take CO2 and convert it into fuel using conventional energy. So in our institute, as a part of the center, we are focusing on using sunlight in order to convert the carbon dioxide to some useful fuels. On one side, you can convert that to formic acid. On one side, you can convert to methane, methanol, everything. And our primary focus is based on photocatalysis and electrocatalysis. On the left side of the slide, you could see that we are showing a simple image where we will use the sunlight, where the energy of the sunlight will be used up to convert the carbon dioxide either to carbon monoxide or formic acid. On the right side, you will see a very complex picture, but it's nothing. It's more like a kind of electrolyzer that we typically have, where we split water to generate hydrogen and oxygen. In this case, we are going to convert CO2 to formic acid or carbon monoxide. So can we move on to the next slide, please, Niket? Yeah. So what we do in terms of this work is like we work all the way from deep fundamentals and to the applied research. So in the deep fundamentals, we go down to the atomic level and we try to tune the metals at the atomic level. One of the class of metals that we are quite heavily investigating is called halide double perovskites. You could see that right there, halide double perovskites. It is a new class of materials that in fact got a lot of attraction back in 2020. So it's like really like last 1 to 2 years, I think its application in photocatalysis have gone up quite much. In fact, this metal started to be in survival since 2009 in the solar cells domain. However, they couldn't make a metal very stable. However, this class of metal based on halide double perovskites, it looks complex, but it's very easy to synthesize. You can dump all the precursors in one go and get the metal out. And here we have two specific elements, which is indium and bismuth. And in fact, what we found out is that this metal, these specific elements are acting as a catalyst, which can serve the conversion of carbon dioxide to formic acid. And in the next slide, I would like to show some quick summary of the results, where we have used these two materials independently, that is the halide double perovskites based on indium. You could see the one in red, which shows the conversion of CO2 to formic acid as a function of time with these catalysts. You could see that, in fact, this is one of the record numbers. In fact, we haven't even published this data yet. This will be coming out soon. This is one of the record numbers, even compared to the state-of-the-art systems. And we also have done the blank ones. You could see at the bottom, there is a circles, black circles. When we don't have this catalyst, there is no conversion of carbon dioxide to formic acid. So it's only the presence of this double perovskites and then the light together helps converting the CO2 to the formic acid. And one thing that we have to really understand, this is one of the fundamental areas we focus on. The other thing that I would like to really highlight is that most of the carbon dioxide research across the world, they use the bottled CO2, which means they use very pure CO2 from the cylinders. And however, when you look at the smoke exhaust from power plants, they always have a lot of particles, including particulate matter, SOx, NOx, humidity, everything will be there together. So typically SOx and NOx are like probably a bit difficult to eliminate at like down to PPT level. I'm talking about the parts per trillion level. So their presence, however, is known to show a kind of toxicity to the catalyst in the fuel cells, especially when you have SOx or NOx. It's shown to become toxic. In our center, we have taken this as a key issue. We don't want to work on like pure CO2 and eventually it doesn't see the light of the day. Rather, we started working on catalyst and understanding what these toxic components in the flue gas can affect. Oh yeah, we can stop at this point. Like, yeah, here you can see that again with the we have developed in-house catalyst with Professor Raghuram Shetty in the institute. So we worked on tin-based catalyst on a copper foam. It's a very high surface area, and nearly we've just matched the Faraday efficiency, which means the amount of current you send into the number of products come out, and that essentially goes above 90%. We could convert almost all the CO2 to selectively to formic acid. This is a very difficult thing. In fact, getting a selective product is fairly difficult. In the next slide, we will quickly show what are the effects when we have SOx. SOx is one of the like a most terrible guy that poison the catalyst. You could see that the first vertical bar, when we use the catalyst with pure CO2, it gives 90% conversion. The moment you put SOx, this SOx guy goes and absorbs onto the surface and eventually killing the performance. Then what we have done is we are trying to find a way how to get this SOx off from the surface. And in fact, we just did purge CO2. And in the third bar, you could see that the performance went back again slightly, but not to like completely back to 90% efficiency. So in our center, we are in fact working on this specific aspect of it. What would be the effect of SOx and NOx poisoning on the catalyst, the long-term performance, and eventually when you scale it up, these information will be quite helpful. This is the activity that we are doing with photocatalysis and electrocatalysis. Now I'll pass it on to the next person on board. Thank you, Niket. You're muted, Jitin.
Thank you, Arvind. So moving on, the next segment is again utilization from a thermocatalytic point of view. So while a wide range of chemicals can be synthesized from CO2, one of the chemicals that has attracted a lot of attention globally and for us in the center is methanol. So this falls within the ambit of converting CO2 to a liquid. So it can be one of those technologies which converts emissions to liquid or gas to liquids. So with captured CO2 and green hydrogen that's available, the process basically involves hydrogenating CO2 in a catalytic reactor to convert it into methanol. Interest in methanol stems from the fact that it's a liquid fuel and it's a bulk platform chemical used for synthesis of a wide variety of chemicals. And all the operations involving use of these chemicals again emit CO2 back. And this whole process, when operated in a loop, brings us back into this whole concept of a circular economy. So with that in mind, what are some of the challenges that are faced by the community in methanol synthesis from CO2? While there are a lot of those spanning different levels and different spheres within the technology front, the few that we are trying to address in this particular center and in our initiatives are listed here. One is the typical problem of converting CO2 through hydrogenation, which leads to a wide range of products. And the one that is of interest to us is methanol. And the unselective catalytic conversion can lead to products as shown here. And these are not the ones that are of interest. So addressing the problem of selectivity to the desired product methanol at high CO2 conversion is one of the challenges that we are trying to address in this center. Many of the catalysts that have been explored for this particular reaction are multi-component, thereby being multifunctional as well. And it also is an extremely peculiar case that most of these materials, which are composites of metals and metal oxides, are not only sensitive to the way they are synthesized, but their surface structure and the active sites on these catalysts are extremely sensitive to how the reactions are carried out and the harsh environment under which typically these hydrogenation reactions are carried out. So our understanding of what we call as the working catalyst is limited because of the fact that these catalysts do undergo significant change during reaction. With limited understanding of the catalytic active sites, our ability to tailor active sites on these catalysts so that we do have specific sites that allow specific intermediates for the desired product is of limited capability right now. So this is another challenge that we are trying to address in the center. So with that in mind, just a quick example to show how the microstructure of the catalyst influences reaction pathways and the desired product. Here is an example. What is shown here is a composite catalyst, and what is shown here is the adsorbed carbon dioxide on the catalyst undergoing a reaction. What's shown here is the final product. The pathway shown here shows different intermediates to get to methanol, which is up here. All of these read on the red side, actually, while it gets to methanol, but also has an intermediate, which is carbon monoxide, which is an undesired product. So for the reaction to be carried out in this particular route, which is shown in green, we need to have specific sites which allow for these specific intermediates to be formed to get to the desired product exclusively. And these are the kind of activities that we're looking at. So the approach that we are adopting to address some of these challenges includes kind of amalgamating a few different seemingly unrelated techniques. One is obviously extensive catalytic reactor experiments. The other is in situ or near operando spectroscopic techniques. And the third is multi-scale simulations spanning catalyst active sites or the atomic scale to the catalyst to real reactor scales. So spanning scales right from atomistic to reactor scale. So once we do this, individually, each of these techniques give us data. Say, for example, catalytic reactor studies give us lab scale data. In situ spectroscopy gives us mechanistic insights. So does modeling efforts. It does give us mechanistic insights. But when we combine the spectroscopic techniques with computational techniques, what we hope to do is to have a mapping of computational as well as real spectroscopic data to unravel the underlying surface structure of the catalyst, which eventually is operando structure determination. So with this, we hope that we are able to develop methods for operando catalyst structure determination using fairly common techniques. Once we have the structure determined using a multi-scale approach, we are also looking at developing validated hierarchical kinetic models, which will enable us to do a computation-aided reaction optimization with the eventual objective of performance optimization for these kind of reactions for very large scale or at least pilot scale studies. So what we are doing in the center is, if you look at it, we do have a fairly heavy fundamental aspect, and we're also looking at using all of the fundamental insights for technology development. And for this, we are trying to work with our industrial partners. Thank you. I'll move on and hand it over to Professor Rajneesh.
Okay, great. Thanks, Jitin. Yeah, so if you have followed so far, what basically we have been talking about is, first we talked about the capture aspect of CO2. Typically, the CO2 does not come in pure form from any point source. So it will always be in a mixture. Either there will be a mixture. So if you're talking about capturing CO2 from a post-combustion capture, so there will be a mixture of CO2 and nitrogen and oxygen, along with some other flue gases. And if you're talking about pre-combustion mixture, then it will be a mixture of carbon dioxide, hydrogen, carbon monoxide, and hydrogen sulfide, and some of the other poisonous gases which comes along with that. So the first step is to capture the CO2 from there, and then you can basically either utilize it or you can sequester it. The scale at which CO2 gets emitted is in gigaton scale. And the capture capacity, the utilization capacity right now, whatever technology we have, is maximum in, say, megaton scale. So there is a huge gap between the actual emission and the technology which is there for utilization of the CO2. So the best approach would be to basically sequester it. And we need a sequestration source which basically is large enough that it can basically handle this gigaton level of CO2 coming out from such point sources. So gas hydrate presents a very clear advantage over there, because under the seabed, we have the right temperature and pressure conditions where gas hydrates can form from CO2, and then it would basically permanently sequester CO2 as solid hydrates. Now, what are hydrates? Hydrates are basically very similar to something similar to ice, where this hydrogen bonded water molecule basically have a cage in here, and inside this cage you can have a CO2 molecule or a methane molecule or hydrogen, nitrogen, whatever, depending upon what gas you use. You can basically form hydrate artificially in the lab, and it also exists under the seabed naturally. Naturally, we find huge amount of methane hydrate under the seabed, and which is also a source of methane gas. So if you see, there are different structures which form depending upon what size of molecule you use for hydrate formation. For example, if you're using carbon dioxide for formation of hydrate, it typically occupies these large cages, completely occupy the large cage of structure 1 hydrate, and also occupies around 70% of the small cages. And that leads to roughly a storage capacity of 30 grams of CO2 per gram of water. So the storage capacity is significantly high. And this also, and since there are different cage sizes, you also see that there's an opportunity to separate a gas mixture. So suppose you have a mixture of CO2 and hydrogen or CO2 and nitrogen. If you form hydrate, CO2 will preferentially go into this structure and will be able to separate it out. The hydrates which we form in the lab look something very similar as ice, and it forms quickly actually. If you see here, we have liquid water and gas in the gas phase, and we just stir it together, and you see that quickly we see ice-like crystals growing in the hydrate reactor. This can be scaled up to whatever level we want, because under the seabed, these hydrates are at very basically in millions of tons and gigatons of methane, which is stored there under the seabed. So the process is very simple. If you have a gas mixture of CO2 with nitrogen or hydrogen, you basically allow it to come in contact with water. Preferentially, CO2 will form solid hydrate, and then that would basically lead to a gas phase which is depleted in CO2 and a solid hydrate phase which is enriched in CO2. If you start with a very lean composition of CO2, then you will have to have multiple stages. So if you start with say 50% CO2, within a stage you will be able to enrich the CO2 to up to 90%. Cost-wise, also hydrate process is not too bad compared to amine process or membrane process, which is more mature technology. So by this, if you start with 17% of CO2 and 83% nitrogen, you basically get to around 98 to 99% of CO2, which is good for disposal under the seabed. Obviously, you will have to, since these are multi-phase, multi-component reactions, you'll have to basically design and optimize your reactors better. So we actually, in our lab, we work on these aspects. We also have a patent for gas acid-base separation process using fixed bed setup. The other topic which I was talking about was the sequestration of CO2 in very large scale. You see, this is a hydrate, methane hydrate, which naturally occurs under the seabed. And this exists for millions of years under the seabed because there is high pressure and low temperature under the seabed. And similarly, if there are places where there is no hydrate, we should be able to basically sequester large amount of CO2, something very similar. You see, this is the window of opportunity that is around 200 to 300 meters below the seabed, where the temperature conditions and the pressure conditions are sufficiently large enough where hydrates can naturally form. So if you can sequester CO2 under the seabed, huge amount of CO2 can be sequestered. If you want to read more about the sequestration of CO2, you can basically go through some of the publications from our research group in the past. So what we basically are trying to say that we will capture the CO2 and by using hydrate, and we can also sequester the CO2 by hydrate under the seabed at right temperature and pressure conditions. So for that, we have a pilot plant in our lab where we have a 10-liter reactor where there is an injection well, production well, and we basically do all kinds of studies to study the rate at which CO2 could be sequestered and study the rate at which it could be dissociated if there are some thermal shock under the seabed. So all these kind of studies are being done in the lab, and this is pretty much what we do in our team in CCUS lab. So now I would expect Professor Praveen Linga to basically moderate the session where first he can ask the question and answers from the team, and then he can take the questions from the audiences.
Thank you, Rajneesh. We had some excellent short sessions from the team CCUS in this seminar. And I have actually written down some questions while the seminar was ongoing. So I would start off with these questions, and I would like to encourage the participants to use the Q&A tab. We have also marked some of these questions, which I would be gradually bringing them up into the session and putting it out to the speakers. First, I would like to start with this question. What are the possible approaches that are to be evaluated or developed under the project for CO2 capture? I see that Prof. Niket touched upon it briefly. Perhaps, Prof. Niket, you can expand on what are the targeted CO2 capture technologies that you're going to look in more detail?
Yeah, thank you, Professor Praveen. So for this question, so the technologies that we are focusing on are physical and chemical adsorption and membrane-based technologies. Right from material development, trying to understand material development experimentally. For example, we are looking at metal organic frameworks, which is a new class of materials that have come up in the last couple of decades. So we are looking at MOFs for CO2 capture. We are looking at polymer inorganic composites, as well as what is known as decorated membranes, as well as MOF-based composite membranes in order to separate CO2 from various other gases. The challenges basically are that there's a whole lot of impurities, for example, sulfur-containing impurities, acidic impurities, and so on. So to maintain stability of this systems, to maintain high efficiency at the low cost is the overall challenge. So that has to be addressed both from material perspective right up to the reactor and system level perspective. So that's what we mean by multi-scale approach. And we do multi-scale both experimentally as well as through simulation. So we're trying to use, so we have people with simulation expertise and experimental expertise who are working together to solve these problems.
Thank you, Prof. Niket. As a follow-up, right, perhaps from based on your response, right, I think a key focus is going to be on developing next generation materials, perhaps as you highlighted MOFs. Do you have any targeted scale that you wish to attain in terms of from a process point of view?
Yes, so we would like to attain a scale of approximately hundreds of grams. That is going to be our target. Yes, of course, from a large scale perspective, that's fairly small. But compared to where we are, which is of the order of hundreds of milligrams to a gram, that is 2 orders of magnitude scale up compared to where we are currently. If we talk about TRL, technology readiness levels, it's TRL 1 or 2 at the moment that we are talking about. So that signifies 2 orders of magnitude scale up that we are trying to target.
Thank you, Prof. Niket. Let me now move the topic towards utilization. We had 2 speakers presenting different aspects of how CO2 could be utilized potentially. So often the challenge between capture and utilization is the scale and speed, right? So this is something that is among the biggest challenges if you want to club utilization into carbon capture technology that we see around. Perhaps your thoughts on that, scalability wise, what challenges you do foresee given the 2 different approaches that both the speakers, Prof. Jitin and Prof. Arvind presented. Can you guys expand on this?
Yeah, sure. So in terms of scaling up, I mean, definitely, Professor Praveen, like we have that big gap between the amount of CO2 that we emit and then how much we can convert it to the useful products. So I think once we develop right technology, which can convert the CO2 to useful products at a mass scale and with good efficiency and using possibly the renewable energy, I think then things will go, the gap between the 2 can be bridged much closely. As of now, I think it's very difficult to judge when that's going to happen. However, based on the way we are approaching the problems, the more realistic problems, like we have talked about, literally not using the CO2 from the pure like bottles with 99% or 99.9%, rather we go ahead using the ones with SOx and NOx. So that because the center is going to be much more realistic. Exactly, I think you pointed out that we're going to bridge that gap sometime soon, with the hope that we will be able to come out with some scientific solution in, let's say, like few years. I think then once the technology is established, bridging the gap wouldn't be a problem. That's the way I look at it. I think we are fundamentally already limited by the stability of the catalyst, for example, how long they can survive. And then once we use it in one place, let's say you have a SOx and NOx poisoning them, can we literally recycle them in order by removing the SOx and NOx from the surface, and then so that we can put it back to the operation. The other problem that comes with is once you convert into product, let's say formic acid, the billions of tons of CO2 we are emitting, we cannot convert all of them to formic acid also. I think we need to split that into multiple things. For example, a portion of it has to go to syngas, because at the end, the final product also should find its users. Otherwise, I think we will not be able to, then we will be accumulating formic acid instead of CO2. I think that's how it's going to happen. So we need to literally spread out across various products. In our lab, like what we are focusing is syngas and formic acid. However, over time, if the cost advantages come over, then we may move to methane and methanol as well, because methane and methanol are like kind of one of the like heavily consumed commodity chemicals. I think that's the way I look at it. So the scientific challenge is what is blocking this gap bridging business. So I'll pass it on to Jitin also. He can give his perspective from the simulation point of view.
Thanks, Arvind. So I'd add on one other point. While we also need to consider the kind of emitting sources, there are certain sources which might be associated with certain kinds of other associated energy forms. Say, for example, there might be sources where you do have energy in certain forms that are available. That will also kind of determine the kind of products that can be formed from that particular scenario. So I spoke specifically about methanol, which is heavily dependent on hydrogen. And hydrogen, as it is currently produced from reforming of petroleum and gas, which is not the route that we want to. So we would have a scenario where we would like to see that the hydrogen is also generated from green processes. There might be other opportunities where you don't have to rely on hydrogen, but there are opportunities to look at non-hydrogen based conversion processes. So depending on the kind of source that we want to apply or utilize these technologies to, so we would also have to tailor the kind of products and specific reaction routes that we are targeting. Although in the CCUS center, we planned to start off with methanol because methanol is one of those big demand chemicals. So in terms of scale, I personally foresee that, we may not be looking at extremely large scales, but kind of tailored to the specific point sources that we are trying to target the technologies to. Preeti, would you like to add something?
No, that's all. I also was going to say that we're looking at this point with the thermocatalytic, we're probably looking at sort of a local solution, not to transport very large amounts of CO2 and then make value-added chemicals from them. So per use to generate the chemical, that's sort of what we are thinking about. But it's early days as well, for sure.
True, and thanks that Jitin, you brought Preeti into the picture. I actually wanted to ask the next question to Prof. Preeti. How can we broaden public awareness of CCUS in India? I certainly think that there is a big gap there. You know, should academic community present a more active engagement, or should we get the industry involved? Your thoughts on it?
Thank you, Praveen. That's a great question. Of course, I think there is knowledge about it, but it's probably sort of misconstrued in various ways as well. And as chemical engineers, we are always the bad person, right? We invented plastics, we put all the CO2 into the environment. If chemical engineers were not there, the world would have been such a cleaner, greener place, is the feeling, I think. But I think we have a very important role to play to marry all these things, you know, the fundamental research that we are all so energetically and actively involved in, developing technology that is relevant, not for the country especially, so that it fits into the equation for us, and working with industry and policy makers. So if we can sort of span this spectrum, get young people enthused to work on this. It's a little dirty. I think I myself work a little bit on coal, and it's the dirtiest thing that you can work on. So if we can get young people enthused to work on this, and then stretch all the way to policy makers to involve with us or involve us in articulating what makes sense for the country. I don't know. I think I'm still very optimistic that change will come and change will be for the better.
Yes, thank you, Prof. Preeti. Rightly, you touched upon your earlier works while you were in IIT Bombay. I think many years ago, I read a paper on your underground coal in situ, right, coalification activities. So yes, definitely coal is considered the dirtiest, but with the adoption of CCUS, perhaps we could paint a much greener color to it, because you cannot run away. We cannot run away from coal until the renewables are going to match up to the demand that is needed. So that's why this project is a critical, solution that several colleagues at IIT Madras are going to work on. The next question I have is again on a general status is, what is the current status of CCUS in India? Perhaps I can request Prof. Sapna to address this if Prof. Sapna, she's in the panel.
Yeah, I'm here. Hi.
Hey, hi.
Yes, CCUS, it's the current status of CCUS in India is not advanced like in the European countries like Norway and US, where the technologies of CCUS is actively working, and a lot of technology, a lot of field work is going on, but still now there are a lot of initiative has been government has started a lot of initiative along with a lot of companies like Tata Steel and also some other companies. So still the initiative going on, and we are slowly progressing towards achieving the CCUS approach, and also the combination of CCU and CCES. Yeah.
Thank you, Prof. Sapna. What the last question I've written down before we go to the attendees' questions is targeted towards Rajneesh. What is the current potential for CO2 sequestration in India, like in terms of the availability of geological formations? I know you talked about hydrates, which definitely is in the long term, perhaps one, but the near-term solutions would be to look at depleted oil and gas reservoirs or geological formations. Do you have any update on? Can you update the attendees on that aspect, the potential for CO2 sequestration?
Thanks, Praveen. It's a very important question. So see, we are in India, we have been utilizing a huge amount of CO2 for enhanced oil recovery. So Keynes oil field in Barmer. They are actively doing this. Most of our oil fields in India are already kind of depleted, and CO2 is being utilized actively in most of the oil field to enhance the productivity of oil for secondary and tertiary recovery of oil. So that's one area where we have been utilizing CO2. It also sequesters CO2 to a certain extent. The other important place where we can basically contribute a lot is in coal bed methane. So basically, if we sequester, we have a huge amount of coal beds all around India, and in fact, coal all around India, and in fact, we are one of the largest producer of coal. So considering that coal is being considered as a dirty fuel, Professor Priti has already talked about it. One option for us is to sequester CO2 in these coal beds, and then that would give you huge amount of methane in return. So the challenge would be to separate a mixture of CO2 and methane, and we are working on that also, because when you're trying to sequester a gas like CO2 to produce methane, you can't get pure methane out of it. You will get a mixture of CO2 and methane, and then the challenge would be to separate this mixture, which is going to again cost some energy and will produce require some energy that will further produce some CO2. So you'll have to do an analysis of it. Now, the next possible scenario would be to basically sequester CO2 in basalt rock formation. We have huge amount of basalt rock formations reservoirs in India. And though the reaction between the basalt rock and CO2 is a little slow, but it gives an opportunity for you to sequester large amount of CO2. And this is an area where we have, in India, we have done a lot of work, NGRI, especially CSIR, NGRI. In Hyderabad, they have done a significant amount of work on Deccan Plateau on CO2 sequestration. They have done a huge amount of sequestration. Regularly, they have also gone and checked the CO2 emissions from those sites where they have sequestered the CO2. So that certainly present a very encouraging picture that we have huge amount of basalt rock formation, and we should be able to sequester CO2 permanently there in these basalt rock formations. And as you have rightly pointed out, that gas hydrates are one of the opportunity for us to basically see here. We have, India is basically blessed with huge amount of methane hydrates, which call it natural gas hydrate under the seabed. Krishna Godavari basin has it, Mahanadi basin has it. Andaman Nicobar Island, the basins in there, they have a huge amount of methane hydrate. So we have been also working on sequestering CO2 in those hydrate reservoirs. The advantage there is that you will be able to produce methane once you replace some of the methane from the CO2. So I didn't talk about in my presentation, but there is an opportunity for us to sequester CO2 in large amount under these methane hydrate reservoir. And in return, we get a mixture of CO2 and methane, which can be separated to produce, basically produce methane out of it, which could be combusted to produce CO2, and every mole of CO2 which you basically produce after burning this methane, you can get a equivalent mole of methane from under the seabed. So this can become a very sustainable approach where you are sequestering methane, CO2, producing methane, getting the energy out of methane, and the CO2 which comes out from the production of this energy again gets sequestered back to produce further methane. So this kind of sustainable approach we are working on, and we have already delivered a project to Gas Authority of India Limited recently, and we look forward to do a field trial in near future. Obviously, this is going to cost some money, but yeah, the government is ready to go ahead with a field trial in near future.
Thank you, Rajnish.
The question rightly, Praveen.
Yes, thank you, Rajnish. I think that was quite elaborated. Let's go to the participants' questions now. I have marked a few. There's one question by Nivesh Oja. Is photocatalytic CO2 reduction performed in the liquid phase? I've actually marked this for Jitin to answer if Jitin is on. Jitin?
Yeah, I'll bring Jitin.
Yeah, this question was posted about the time when you were presenting, so I just marked your name there. Yeah. Is photocatalytic CO2 reduction performed in the liquid phase?
So can I hand this over to Professor Raghuram Chetty, because he is the other colleague who is handling the photoelectrochemical system along with Professor Arvind. Professor Raghuram?
Yes, Prof. Raghuram. He's there in the audience. Is he there in the panel? Yes, I saw him. Okay, in the interest of time, we'll give him a chance to come back. There's one question on the cost and energy. Perhaps I can trouble Prof. Niket for this. The question related to this is, The question is by Pritesh Jain. Would love cost and energy comparison. The cost fraction of revenue from power produced. Basically, I think the question is targeted towards energy penalty. What would be the energy penalty that power plants, perhaps I'm going to expand that question and pin you down on this because power plants are the largest point source emitters. Can you comment on the current energy penalties that GenPost will have to?
Yeah, Praveen. I think rough figure we can say around 20 to 30% would be the energy penalty that one would need to pay. So again, I mean, so that's the overall point that I was trying to raise. Basically, was that there's no free lunch, and that there will not be a silver bullet type of solution. So a lot of times, and again, that comes back to your question about whether the scientific community needs to. And I'm sorry, Praveen, I'm broadening the scope of the question over here. But one of the things that we discuss is, as a scientific community, how we can reach out and we can broaden the perspective and educate people and educate ourselves also. So yes, we are going to pay the energy penalty. If we want to maintain the lifestyles that we maintain, that penalty is going to happen. But the other thing, so for example, one of the examples Rajneesh was giving was methane to CO2, right? So sometimes suddenly the question pops up in people's mind that, there's methane and then you're converting methane to CO2. So aren't you doing net zero? But we actually are not, simply because methane is one carbon and 4 hydrogen atoms. So in addition to forming C to CO2, which gives energy, there's also hydrogen that forms water, which is cleaner than C to CO2. When we talk about all of these, we are talking about a different area of research that's called the life cycle analysis as well. So if you have that broader perspective, there is a very large space where all of this can operate. Coming back to the original question about the energy penalty, yes, we are going to pay that energy penalty for reducing the amount of CO2. Why do we need to pay that energy penalty? Is because we have this fossil fuel, which is an excellent source if we are talking about energy only. Okay, but it's not a great source because we have other pollution that comes in. We have CO2. And CO2, I would say, is not a pollutant. Again, that is something for people to realize. CO2 is a greenhouse gas, which is not the same as a pollutant. NOx is a pollutant. Sulfur oxides are pollutants. Hydrogen sulfide are pollutants. CO2 is a greenhouse gas. So the best thing that we can do if you have a carbon-based source is to completely convert to CO2. But we don't want so much CO2 in the atmosphere. So what do we do with it? We need to convert it back through the various technologies that we talked about, or we want to sequester it into underground sources. And that requires that energy penalty of approximately 20 to 30%. And I think on one of the slides, I don't know if I'm sharing that slide.
I think the number is about that range.
Yes. So I think Professor Rajneesh had gone over that. Slide.
Thanks, Prof. Niket.
Sorry for broadening that question.
Excellent, actually. I think it's important. Life cycle analysis is a key aspect. And even many of the sequestration projects that are being undertaken in Norway and US, per se, they are putting in long-term risk management strategies, to looking at maybe perhaps 10 years, 50 years, 100 years, what's going to be the fate of these sequestered CO2. There's one very good question related to chemical engineering discipline. All of us are in this. So that's by Suraj Reddy Chamakura. Just like in a chemical reaction, there is a rate determining step. When talking about CCUS technology, which of these three processes, capture, utilization, and sequestration, is the RDS or rate determining step of the process, according to you? So I'm going to put this an open question, so any panel members can take it.
I think different people might have different perspectives. One. Second is the rate determining step. I would also think will keep it's both temporal and spatial, in the sense that the answer would change from place to place and from time to time. So Today, I would say probably capture is the rate limiting step. Because if you look at the commercial technologies, the primary commercial technology is a mine-based technology. But if we are using it for CO2 capture, we are going to pay a huge energy penalty with it. Comparatively speaking, the energy penalty with the other technologies are lesser when it comes to sequestration or conversion or utilization. But again, I would think, it probably would go around in cycles. So, as we try to solve one problem, the problem will get shifted with respect to the rate limiting step and another step becomes rate limiting. That would be what I would say. But as of now, I would say capture. I don't know if other panelists have a different view about it.
Thank you, Niket. Because I think the second part of the question by Suraj was to look at which of these three requires intensive research. The answer was already given by Prof. Niket. It depends, and right now the focus is on capture because you need to bring the cost down for the capture, as well as there is a huge level of funding around globally for utilization now at the fundamental level, as highlighted by two excellent speakers, young colleagues in IIT Madras by Arvind and Jitin, where they're looking at the fundamental breakthroughs needed for the utilization part. We still have time, so there's lots of questions still coming around. I'm going to pick a few more questions before I wrap it up. There's one question on hydrates. Perhaps I can call Rajneesh back. Though, since I'm a moderator, I will refrain from answering questions related to my field of research. How can CO2 hydrates be useful? Can CO2 hydrates be useful as a renewable source for sustainable development or circular economy? Rajneesh, I'll let you take this.
Yeah, actually, I have already answered that question, but I'll repeat that. Obviously, carbon dioxide cannot be a source of energy. See, there is nothing in CO2 which can basically burn. It's already a product of combustion. But what I discussed in last time when I was here is that you can use CO2 to produce methane either from coal bed methane or from hydrates, the natural gas hydrate which is under the seabed. So as I was telling you that in hydrates specifically, if every mole of CO2 which you sequester there, you get 1 mole of methane coming out of it. So in a sense, if you talk about circular economy or sustainability, I would say is that you are capturing CO2 there, and every mole of CO2 which is captured, you get 1 mole of methane, and which you can basically utilize to produce energy. And the CO2 which comes out of it, you can again sequester it and get 1 mole of methane if this technology works well. That is something which, in coal bed methane, it works quite well. There is no problem. But the challenge again is the separation of CO2 and methane. And that brings a challenge. And this is why what Professor Linga and Professor Niket has talked about, that the capture is the biggest bottleneck right now. If we cannot capture CO2 from a mixture of CO2 and methane at a very, say, economical price, then we will not be able to use any of this technology. So first challenge is to basically bring down the cost of capture of CO2 from its associated gases, whether it is CO2 and nitrogen, whether it is CO2 and hydrogen, or whether it is CO2 and methane. For example, CO2 and hydrogen can be separated if you can use coal for gasification, and water gas reaction will produce a mixture of CO2 and hydrogen. And if you have a technology which can, basically economical technology which can separate the CO2 from the hydrogen, you would be able to basically use hydrogen as an energy resource. And hydrogen is much better energy resource compared to methane because there is no carbon in hydrogen. So yeah, means in a sense, CO2 can be utilized for producing energy, but yeah, CO2 itself is not a source of renewable energy or energy.
Thank you, Rajneesh. There's another question related to capture technologies. This question is by Mahendra. What is the pilot scale demonstrated? I think the question is targeted towards, is there, perhaps I'm going to add words into that, is there a pilot scale demonstration planned in India? Because globally, yes, there are more than 25 active pilot scale or near commercial scale technologies for demonstrating CO2 capture, as highlighted by Prof. Niket as well. Most of them are targeted on amine-based separation process. So is there any pilot scale, industry-funded projects on CO2 capture in India right now?
NTPC has a couple of plants running on amine-based process. There are many specific companies which basically are specialized in CO2 capture. There are many Indian-based companies which does this CO2 capture in different parts of the world. See, the challenge in India is about the policy. The government policies should be such that the cost of CO2 capture or the demonstration of CO2 capture from this flue gas and fuel gas should be somehow compensated by the policies of the government. That is right now not there at that level. And this is why most of the companies which is operating in India, they are basically doing the pilot planting in India, but they are basically delivering those technologies to European countries. So there are Lanjatech, for example, another company which is also talking about utilization of CO2 by fermenting CO2. Now, this is something which is they are doing it at large scale, and they plan to do it ferment CO2 in large scale to produce valuable chemicals and fuels out of it. So there are multiple companies within India who are doing wonderful work in this particular domain.
Thanks, Rajneesh. There's one more, maybe perhaps a last question that I could take. This is on utilization. Let me see. I narrowed down the question. Where is it? Yeah. So this question is by Smriti Purohit. How to tune the selectivity property of photocatalyst for emission of CO, methane, and other products using CO2 reduction? Perhaps Jitin can take this last question.
Yeah.
So I'm not an expert in the photoelectrochemical front, but I could still take a try at this because I work on the catalytic front. So one of the aspects that would really tune the selectivity of the products that you have is the nature of the materials by themselves. If you have a combination of materials and if you have certain types of active sites which enable certain kinds of interactions between the reactants or the intermediates that form as a result of the initial reactions, those are the ones that typically allow for the reaction pathway to go in a particular route leading to certain specific products that are desired. So the difference when you have a photoelectrochemical process versus a thermocatalytic process is the driving force. Basically, in a thermocatalytic process, the energy comes from thermal energy, and the other is the energy driven by photons and electrons. So the fact that primarily determines the selectivity is how the species interacts with the materials. So there is a lot of materials engineering for the specific targeted products that would be required if you are to tune selectivity towards desired products.
Thank you, Jitin. In the interest of time, we have to close this session. It was my pleasure to spend this evening with a group of eminent and top researchers in IIT Madras, and I wish you all, the team, the best. And I pass the session to the closing to Preeti or Rudra.
I don't mind thanking you, Professor Praveen. Thank you so much for such a patient and lovely handling of it. I know that if we had reversed roles and you had answered the questions, some really interesting insights would have come up for the audience as well. But maybe this is an opportunity that we shouldn't let go of. We'll do it next time for sure. Thank you so much.
On to you, Rudra.
Thank you, Professor. Indeed, to say the session was really went great. And as Professor Preeti told, there is a prejudice among everyone that the chemical engineers are always considered bad because they have invented plastics and other things. But at this moment, we should also have to understand that the same chemical engineers develop economic ways of using materials and energy. Chemical engineers use chemistry and engineering to turn raw materials into usable products such as medicine, petrochemicals, and so on. And a strong note that they are also involved in the waste management and research, which is much needed for the world right now. So thank you, professors, once again for giving the best thoughts on the carbon dioxide and capture, utilization and storage. Thank you, participants. See you in the next webinar. Thank you.